All right, welcome to section 6.5. Now we're talking about the average value of a function. So, as you might expect, we are going to be talking about the notion of average, or more accurately, mean. And we're going to define the average value of a function as a quantity interpreted as an integral. So, I have here in front of me an example of a function that is non-constant. And to really understand average value, we should define it. So, definition. The average value, which is a real number that we're going to denote FAVG, is the mean of all y equals f of x for x between a and b. So over that entire interval, we're talking about the average value. And so that might be the average value for this particular function. You would expect that if a function is constant, then it should be just that function value. But how do we actually find this value? We know how to do this for finitely many function values, right? So if we build our intuition, right, think about what average means, right? So recall that for a finite number of items, right? So for finitely many x sub 1, x sub 2, ... x sub n, okay, then the average of these function values evaluated at those points would be, I'm going to put a bar above that just to indicate that this is for a finite amount of these. It would be f of x1 plus f of x2 plus ... plus f of xn divided by n. Okay. We can apply this idea and extend it to the infinitely many concept, because there are infinitely many x values between a and b. So we're going to subdivide a and a to b into n subintervals of equal length. And this is going to be important, so I'm going to write it out again. Delta x equals b minus a over n. And importantly, I can rewrite this as delta x equals 1 over n times b minus a, which means that 1 over n is the same thing as taking your delta x and dividing by b minus a. Okay, that'll be important later on. For now, if we take sample points, x sub I star, then we approximate the average value of f as the sum. So I'm using the sigma notation now to indicate, just to make it easier. But it will actually end up looking the exact same as so this formula right here actually matches this formula, except this time we're talking about, this is actually going to be an approximation, okay? Now I'm going to write this by writing the 1 over n in front. So 1 over n times the sum of these function values. Y equals 1 to n. Remember that 1 over n, we said that that is the same thing as delta x over b minus a. And because delta x is constant, we can pull that inside the summation, which means we actually end up with 1 over b minus a and the sum of f of x sub I star delta x. But should this look familiar to you? I think it should be, because in the limit, so as n approaches infinity, this means, formally now, the average value of this function is going to be 1 over b minus a times the integral from a to b of f of x dx. In other words, the average value of the function is going to be the area under the curve over a to b divided by the length of the interval that we're defining over. So formally what we're looking at then, if you want to understand this picture intuitively, we're saying the average value of this function, whatever it happens to look like, right? Maybe it looks like this. And we're looking specifically at this segment here. The average value is, you take this area, you can call it A, and divide that by the length L. And that gives you the average value. Weird, huh? Okay, so let's actually do something with this. So we'll find the average value of a function that we know and love. So our basic example, find the average value of sine, literally f of x equals sine of x, over the interval 0 to pi over 2. Now remember that from 0 to pi over 2, sine reaches a maximum height. So the picture that we're actually looking at here pi over 2 reaches 1. This is y equals sine of x. And we know then that the average value must be somewhere in here. And for the sake of, let's suppose it looks something like that. We're guessing. Don't know. But let's set up the integral then. So f, the average value of sine over this interval, is going to be 1 over pi over 2 minus 0 times the integral from 0 to pi over 2 of sine of x dx. Now, the front part, the fraction here that I have, is going to turn into 2 over pi. And the integral, of course, is negative cosine of x from 0 to pi over 2, sorry. Which means we have 2 over pi of negative cosine pi over 2 plus cosine of 0. Now, cosine of pi over 2 we know equals 0, and cosine of 0 equals 1, which means this whole thing reduces to 2 over pi. Oh, actually, I meant to do this. Whoops. Not too bad. We can generalize this to more application style questions. And we're coming now full circle, basically, to the the question that we posed in the very beginning of the course, which is we were talking about blood in a blood vessel and the flow of blood. That's not how you spell vessel, sorry. So go back to that very first chapter opener. And so we're going to find average velocity over the interval r being from 0 to capital R for blood in a blood vessel, where we modeled that velocity where at some radial distance from the middle of the cross section, we have P over 4 nu L capital R squared minus little r squared. So to remind you again of what we're looking at here. Here's our blood vessel. So if this is the middle, the very middle, then this distance is capital R. And for some given point somewhere in there, we measure the distance from the center, and that's little r. And so the velocity of blood traveling through that, in that distance from basically anywhere along this ring here, any blood traveling in that ring is going to travel at that velocity. And what we saw experimentally is that as you got closer to the blood vessel wall, it slows down due to a phenomenon of laminar flow. So if you're curious, laminar flow. And so to find the actual average velocity, then, we're going to be performing the calculation. 1 over r minus 0, the integral from 0 to capital R of P over 4 nu L r squared minus little r squared dr. Okay, not too bad, right? So what we can do now is simplify the front part. So 1 over capital R times, pull out the fraction here. This whole expression right here can be pulled out as P over 4 nu L, because these are constants with respect to the integration. And then we're just looking at the integral of capital R squared minus little r squared. Capital R, again, is a constant, so that means that this, when we integrate it, is going to turn into capital R squared times little r. But little r squared is going to turn into r cubed over 3. And so we end up with P over 4r mu L times capital R squared little r minus r cubed over 3 from 0 to capital R. We'll need another page to finish this up. And if we use FTC2, then we get, notice that if you plug in 0, that again is not going to contribute anything. So P over 4 capital R nu little l times r squared times capital R is going to be r cubed minus r cubed over 3, which of course gives us with 2/3 r cubed, P over 4r nu L times 2/3 r cubed. That means we're going to cancel this r with this, and that's going to turn into a 2. Finally, that means the average value, the average velocity of a blood cell traveling through that blood vessel is going to be PR squared, P being the pressure differential, R being the radius of the blood vessel, over 6 nu, nu being the viscosity of the blood, and little l being the length of that blood vessel. That's our answer. In the next video, we're going to discuss the mean value theorem for integrals, which is a fun theorem that is actually not too dissimilar from the mean value theorem that we've already explored in Calculus 1. And all we really need to add to that is to connect average value of a function to the fundamental theorem of calculus, and we'll see a very similar or a very exciting result for